Today we're going to start by looking at an example of how we can convert a game which is presented in strategic form into a game presented in coalitional form. Remember from what we said last time that some information will be lost. When we present a game in coalitional form by basically just listing the players and telling the value of each individual coalition, uh, we ignore that information about exactly who contributes what to this coalition. We just care about each coalition's uh, total worth, and by worth I mean the amount that that coalition working together against, say, everybody else in the game, the complement of the coalition, how much that coalition can guarantee for itself as a coalition, the sum of all the payouts for every member of the coalition. So remember, a coalition is just a set of players, S, contained in N here. N is the set of all the players in the game. N is just this set of players, 1, 2, up to N. So S is a subset. V of S, which we'll think of the value of that coalition S, we've already said, is the amount that that coalition S can guarantee itself. So we think of having a two-player game, S as one player and the complement S bar here as the other player, and we ask what is the value of that game to the coalition S. Now, presenting a game in strategic form can be quite awkward because you have to tell the payouts to every player for every possible set of choices of strategies for each player. For example, even in a game with only 3 players, where each player has 2 choices, there would be 2 cubed or 8 possible payout. There are 8, not 8 possible, but 8 total payout situations, depending on the 8 possible choices for one pure strategy for each of the players. And if we were to do what we did with 2-player games, where we listed that just in a matrix, a 2x2 matrix, we called it a bimatrix, as each entry was a pair, we would go naturally to 3 dimensions and make it a 2x2x2 cube, and each entry would be a triple, telling the payout to each player. Instead of going up into 3 dimensions, another choice would be to just list the 2 layers. For example, here, if player 1 chooses choice 1, say there are only 2 choices for each player again. Here we have the matrix that represents the payouts for each possible choice for players 2 and 3. Remember, this is all given that player 1 chose 1. And here we have a 2x2 matrix whose entries, again, are triples. They tell the payout to player 1, 2, and 3 in each entry. And then we separately can list the payouts if player 1 chooses choice 2. And then again, for any choice of 2 and 3, here 2 is the row player, 3 is the column player. Each has 2 choices. We have the matrix, the 4 entries here, each one of which is a triple, again telling the payouts for players 1, 2, and 3. So all of this information tells you exactly what will happen for any choices for players 1, 2, and 3. To convert that to coalitional form, we want to tell you the characteristic function, V here, and we start with the things that are easy. V of the empty set, if no players are playing, that gets a value 0. And V of the entire set of players, N, which is the set 1, 2, 3. We ask what's the largest that the 3 players together can get as a return. And for that, we just add up the 3 entries here. The 3 players together would get 4 if they play. Player 1 chooses 1, 2, and 3 also choose 1. They get 4 total, the 1 plus 2 plus 1. You can look at every entry here and you see the highest total is 5. If player 1 chooses 1, player 2 chooses 2, and player 3 chooses 1, they get a total of 5 units as a payout. How can we find some of the other values? Well, let's look what is the value for player 1 as a coalition with just the one person. Well, to find that, I'm going to go over here to the right. We can look at the payout matrix where player 1 is playing a 2-player game against Now the coalition of players 2 and 3. Now this coalition has 4 choices. The 4 choices are 1, 1, that means 2 plays 1 and 3 plays 1. There's 1, 2, 2 plays 1, 3 plays 2. There's 2, 1, and there's 2, 2. Player 1, of course, has just the 2 choices, 1 and 2. And then we can just put in what the payout to player 1 is in each of these situations. So here, if we have 1, 1, 1, that would correspond to this upper left in player 1 chooses 1 table. Player 1 gets 1. In the 1, 1, 2, that corresponds to this second entry here. Let me use some green here. And we'd get a 0. For 1, 2, 1, we'd have player 2 choosing 2, player 3 choosing 1. Here we'd have a 3. And for player 1 chooses 1, and 2 and 3 choose 2 and 2. We have 2 and 2, a 1 again. And we can just fill out the second row by doing the same thing in this second table here, where player 1 chooses 2. If player 2 and 3 choose 1 each, we have a 0. If it's a 1, 2, that corresponds to the upper right here, where we get a 2. If it's 2, 1, we get the 3 in the lower left. And for 2, 2, we get a 1. And then we ask, what can player 1 guarantee here as a maximum expected return in such a game where player 1 is playing against 2 and 3? Well, we solve this as if it were a 2-player zero-sum game. And we can do that very easily here because it's easy to see that column 1 dominates columns 3 and 4. That 1, 0 has smaller entries than the 3 and the 3, or smaller than or equal to here than the 1 and the 1. So we can reduce to just a 1, 0, 0, 2. I won't put the labels here, but that's row 1 and row 2 represent choices for player 1. Column 1 and column 2 represent these 2 choices, 1, 1 and 1, 2 for players 2 and 3. It's easy to see the value of the game. We don't even need to worry about optimal strategies here. You can just use our formula for the values of a game here. There's no saddle point. We can find the value to be just 2/3. That tells us that the value of the coalition containing just player 1 is 2/3. Let's go through one more example and ask, what is the value for a different coalition? Let's say we have the complementary coalition 2, 3. So players 2 and 3, or I should write this using the notation here that we've been using. Actually, we're using this notation now, just regular 2 and 3. Players 2 and 3. What is the value here for that coalition? Well, we want to look at a different matrix. We want to look at the matrix where 2 and 3, for some reason I'm writing them with Roman numerals, that's not necessary. Here we have players 2 and 3 playing against player 1. But now when we make the matrix, we want to ask, what is the total return for the coalition of players 2 and 3 compared to, I'm sorry, the total return for the coalition of players 2 and 3, given the different possible choices. Remember, 2 and 3 can play choices 1, 1, that means they both play choice 1, 1, 2, 2, 1, and 2, 2. Again, player 1 can just play a choice of 1 or 2. And we have to look and see what those entries are. So if player 1 plays 1, players 2 and 3 also play 1, we're in this upper left entry. That gives us this, this position in the original strategic form, where player 1 gets 1, player 2 gets 2, and 3 gets 1. The total for the coalition of players 2 and 3 is that 2 plus the 1. So we're going to enter a 3 here. I'll put these in green now. if player 1 plays 1 and 2 and 3 play 1 and 2, player 2 plays 1, 3 plays 2, we're now looking at this upper right entry in this table, and the coalition of 2 and 3 gets a total of 1 unit. It's easy to see that if 2 and 3 play 2 and 1, then they get 2 here, and if they play 2 and 2, they get a total of 1. If player 1 plays choice 2, we're down here in the second table, and we add up, again, the entries for player 2 and player 3. We get a 4. Here we get a 1. Here we get 0. And here we get a 3. And then we solve this game. Now this game also is relatively easy to solve, in fact quite easy to solve, because row 1 dominates all the other rows, and then column 1 would dominate column 2 once that's done. Another way to say that is that there's a saddle point here. This 3 is a saddle point, the smallest in its row and highest in its column. So the value is just 3, the value at that saddle point. So what is this telling us? This is telling us that in this game, player 1 working just by himself can guarantee an expected return of 2/3. Players 2 and 3 working together, just 2 and 3 together, can guarantee at least 3. If all 3 work together, they could get 5 units together. So that tells us that there is some advantage, for player 1 not to be playing separate from players 2 and 3. If they do that, they can guarantee only these smaller returns. Now I haven't listed all the rest of it. To finish out the description of the characteristic function, we would also want to compute the value for the rest of the coalitions. And you can do that all in the same way that we just did, so I'm not going to do that all here. You want to find the value for 2 by itself, the value for 3 by itself, and the value for 1 and 2, as well as the value for 1 and 3. So I haven't listed those. I've just kind of given half of the values for the characteristic function, but you can compute all these very easily just doing the same things we did here. Now, another goal for today's talk is to talk about new definitions that we're going to be using for the rest of this week and, of course, next week. We say a game in coalitional form is constant sum if for any coalition S, the value of S plus the value of its complement gives us the full value, V of n, the value of the full coalition, or the grand coalition. And we'll consider the grand coalition the set of all players. And if that's true for every coalition, we call it a constant sum game. If that constant, which is the sum, in other words, the value for the grand coalition is 0, we call it a zero-sum game. So in a zero-sum game, you can think of it in this way. Any coalition competing against its complement, meaning all the other players, will receive an amount where a coalition gets some number, and that comes from the opponents. So you can think of it as a game where any coalition plays its complementary coalition, and there's just a transfer from one side to the other. If that happens for any coalition, then the sum is always going to be 0, and we'll have what we call a zero-sum game. Now, we saw an example of a constant sum game in the previous lecture. For example, the game where there was a pot of gold that 3 people found worth $4 million, and any 2 of them could betray the third one and take the pot of gold. So the value for any coalition was the full $4 million. If that coalition had 2 or 3 of the 3 people, and the value of the coalition was 0, if it had 0 or 1 of the people. And for any coalition, then the value of the coalition plus the value of the complementary coalition was exactly $4 million, which was the value of the grand coalition. So that was a constant sum game. It certainly wasn't a zero-sum game, because the grand coalition could just take the pot of gold, and that was worth $4 million. If we look at the game above here, we see it's not a constant sum game precisely because of what we were discussing. The value for the coalition containing just player 1 is 2/3 the value of the coalition containing the complement, players 2 and 3 is only 3. Their sum is 3 and 2/3, which is certainly less than the value of the grand coalition. We can talk about payoff vectors after a game is played. Now, those payoff vectors could come straight from the table of original payoff vectors, or they could be payoff vectors that come after a transfer payment is made. We'll say a payoff vector is group rational or efficient excuse me, if the sum of the entries, the sum of the amount of payoffs to each person, is equal to the value of that grand coalition. For example, in this game, we saw the value of the grand coalition was 5. Any suggested payoff to the whole group of players 1, 2, and 3, which totals 5, is what we call group rational. As a group, they can't do better than that. If you have a payoff where we say, let's play the game, and player 1 ends up with 1, player 2 ends up with 2, and player 3 ends up with 1, they only get 4 total, and as a group, they could do better. So that payoff is not considered group rational. A payoff vector is said to be individually rational if each player gets at least the amount that he could get working on his own. V of the singleton set I is the amount that player I could get, at least as an expected return, working all by himself, playing against all the other players. And if the payoff to player I is bigger than that, that at least is something rational for player I. If the payoff is smaller, why would player I want to accept such a payoff? He could just work all by himself and get a larger amount. So, for example, in this previous game, we see player 1 has an individual value, the value of that singleton coalition, of 2/3. If the player said, let's look here and take a payoff of 0.004, we've already said that's not group rational, but that's also not individually rational for player 1, or you could go through all this and see player 2 would also find this not individually rational. Player 1 would never want to accept that. Player 1 would say, okay, forget that plan. I'll just play my own game and get at least 2/3. That's better than I would get for this payout vector. An important thing that we're going to be talking about over the next week is what we call an imputation. An imputation is a payoff vector that's both group rational and individually rational. We've already seen that it won't make sense either to the group or to individual players if you don't have both of these features. So an imputation will be thought of as a payoff vector that at least makes sense for the group and makes sense for each individual player. So the set of imputations is the set of all possible payouts, which are group rational. They get the highest possible total that the grand coalition can achieve, and each player gets more than his individual worth, meaning the value of the singleton set with just that one player. A few more definitions. There are lots of definitions here, and it'll take a while for us to see examples of all of these. When we have a game in coalitional form, we'll call it inessential. Think of inessential as being kind of uninteresting. Inessential if the sum of the values of the singleton coalitions, the sum of the values for each individual player, is equal to the value of the grand coalition. Why is that something we want to call inessential, or I would call it uninteresting? Because for such a game, if each individual plays entirely by himself, you'll see that all the people together get the highest total they can possibly achieve. There'll be no benefit for any player or group of players to form coalitions bigger than size 1. In other words, form any coalitions with other players, because that won't gain them anything. we say a game is essential, that's the opposite. That would be an interesting game. If this equality is not true, in other words, the sum of the values for the individual players is less than the value of the Grand Coalition. I should remind you there's no way we can have the sum being greater than the value of the Grand Coalition because of this superadditivity feature. Whenever players get together, they should at least get the sum of their individual values, or whenever you have two disjoint coalitions working together, they should always receive at least the sum of the values that they could get by themselves. But if the sum of the individual values is less than the value of the Grand Coalition, then the individual players can do better by forming various alliances or coalitions in order to come closer to this higher total. And of course, eventually, if they all get together, they get that higher total. So if a game is inessential, that means basically no coalitions make any sense except individual coalitions. Then there's only one imputation. The only imputation that's possible is to pay off each player their individual values. Why is that? Well, to be individually rational, each entry here has to be at least the individual values. So you would need at least this much in every entry. But there's no way you can have the total larger than the value for the Grand Coalition. So if the sum of these is equal to the value of the Grand Coalition, each one will have to be exactly the value for the Grand Coalition. And as an imputation has to be group rational, which we know this one will then be. The sum of the values will be exactly the maximum total, which is the value of the Grand Coalition, n.